black squares. How's everybody doing? Good. So I'll take a silence as a vote of things are going just fine. So someone chatted in a question, and I realized like when you don't see the chats that might have been there until after you've joined the room. So the question was, when you're working on your homework with normal distribution, should you be using Z tables or R? It's a good question, and you're welcome to use either way. I would encourage R since we're going to be using that more often. That was kind of the emphasis of the reading quiz. But yeah, if you want to use the Z-scores and the standardized normal distribution table, that works too. So either way is fine as long as I am seeing justification for how you come up with your answers. Okay, so before we get started, just want to point out a couple of things on Canvas. So here was the quiz from Canvas, which was making sure that we are able to do these things in R. And then the last question was relating to properties with random variables and expected value. So if X and Y are random variables that are not independent, then we can't use this property over here. The top property doesn't follow, which means this one doesn't follow as well, because this is basically saying the same thing, except X and Y are both X in that case. But all of these are fine. So regardless of what is true about our random variables, independent or not, we can break up sums and we can pull out constant multiples. So we can say expected value is linear in that sense. Any questions about that? And otherwise, we've got some exciting news coming up, right? We've got an exam next week at this time will be our first exam. So to get an eye towards that, I did put a module up in Canvas relating to the exam. There's going to be two parts to the exam. We can talk more about this on Wednesday. There's going to be some multiple choice questions and a Canvas quiz, and then there'll be a written portion that'll be similar to like how you submit your homework, where you'll write it out and then upload a PDF. So next Monday, it is expected that everybody is here on Zoom, even students that are not normally coming to Zoom but watching the recording. So the exam is going to be done on Zoom with cameras turned on. So I'm very much looking forward to seeing everybody on next Monday during Zoom. I added some materials here if you want to start practicing for the exam. So here is a formula sheet that I just kind of filled in the first one, but if it were me, I would like to have a handy list of all of the distributions that we've used and some like what is the PDF, what are some of the shortcuts, what are things that work in R. So you're welcome to use notes during the exam. So in that sense, I'll let you create whatever formula sheet you find most helpful. And there's another document. This just gives you a list of the various topics that we've covered in what sections of the textbook. So if you just want to make sure you're checking off all of the concepts that we've covered, they're listed over here. Again, this is just like a list of topics. It doesn't necessarily go into any of the examples. And then the best way to practice for an exam where you're going to have to solve problems is to practice solving problems. So here's a sheet of just some practice problems. I don't want to call this a practice exam because it's not indicative of the length of your exam and it doesn't cover all of the questions that might be on your exam. But here's just some additional problems if you want to get some extra practice. I do think it's important to not just go over and redo problems that you've done for homework, but be sure that you're trying to practice different problems that you haven't solved already. And I will put solutions to those up so you can check your work. And then, yeah, I think that's it. So those are all of the practice materials for you. And there is one other link over here that has additional practice problems that are listed from the textbook. So if you want some additional problems to practice, here are odd problems that are suggested from the text that you can check your answers. Because they're odd, they have the answers in the back of the book. Okay, so I am expecting that we'll talk about the exam on Wednesday. So if you have like real specific questions, you can hold on to those maybe, but anything that you can think of about the exam that you want to ask about for now?
We can use notes on the exam, right?
Yeah, so you can use notes during the exam. That's right. You're not allowed to use the textbook. You're not allowed to use the internet or anybody else's notes, but anything that you create, you're welcome to use during the exam. Yeah. Okay, so yeah, then the next thing I just want to mention is today we're going to wrap up the probability portion. So the exam is going to cover everything up to including what we talk about today. We're going to start a little bit next time talking about the statistics and the first couple of chapters in the statistics textbook, just to get us going a little bit, and then we'll spend the rest of the time reviewing. So just so you know, like the reading materials from here on out, as you can see here, are referring to a different book. So that's this one over here. If you can see, this is edition 2 of the book. And they do now have the second edition in the library. And so if you want to check out the textbook, there's a link over here that says link to library copy of this. And if you click on this, you might have to like log into your single server identification, you know, but it takes you right to the book. So you can access the book for free through the library. Just keep that in mind. I think if you want to download things, so you can view it as long as you have an internet connection. If you want to download things, I think you are allowed to. There is a button that says download or save pages or print pages, but I do think you're limited to how long you're able to. I don't know how they monitor it, but there might be some limitations to that. Just keep that in mind. You certainly can get it online for free. If you want to purchase it, it's not the most expensive book. Does anyone know how much it goes for these days? I don't know if anyone's bought it. I did put a link to Amazon over here too. I don't work for Amazon. That's what most people get things from these days. Yeah, so $60 to rent it, $130. Okay, it's more expensive than I thought. $130 to purchase it new. Again, you can get it from the library as well for free. Okay, any questions? Okay, and then one last announcement, and then we'll get going, is so for Wednesday, you've got a quiz. That quiz is going to mainly just making sure that you've got RStudio working correctly. We're going to be using RStudio in class on Wednesday. And there's also a course evaluation up here. This is not like an official university one. This is a course, a survey that I put together on Canvas. And it's just nice to get some feedback from all of you about how you think the class is going for yourself, and some reflections about like what are some things that you're doing for the class that are working. So this is really useful for me to hear from all of you. This is anonymous. I won't know who says what. So in that sense, I can't give you credit for doing it because I won't know who did it and who didn't do it. But if I get 80% of you to respond, then I'll give 2 extra bonus points on your first exam for everybody. So please do check this out, complete it before Wednesday's class. That would be great. And then, yeah, the homework 4 is up. Don't forget your 3rd homework is due tonight. Homework 4 is up, and I'm not going to collect it because it's really useful to get feedback on it. And we've got an exam on Monday. So I'm not going to say that you shouldn't do the homework. You should do it just as seriously as if I were collecting it. I'm going to put the solutions up, and you should grade your own work. So although it's not graded, this content will be on the exam, so it is definitely important that you put some time into that homework assignment. But that's up online. Just be aware that it's not going to be collected. So that's why there's no assignment corresponding to homework 4.
I have a question about
Yeah.
homework 3. Are you going to have a chance to grade that before next Monday so we can have feedback?
Yep.
Okay.
Yes. So yeah, your homework 2s are graded. I got those up over the weekend, and I will definitely get through your 3rd homework assignments before Monday. I won't get it done. Like it's not due until tonight, so probably not towards later in the week. But I'll definitely give you some feedback on it before the exam.
Okay. Thank you.
Yep. Okay. Anything else? Okay. So then I want to take a look at some of the material in chapter 4 of the statistics text. So in particular, what we do when we're dealing with generating random samples from a population. So what we're essentially going to be doing, in case you're kind of curious, what is the difference between probability and statistics? So like probability assumes that we know what the makeup of the population is, and then we can calculate how likely is it that we get certain samples. Like for example, we might know how many red balls and black balls and blue balls are all like contained in a bag. And then we can come up with how likely is it that we pick one red ball and one blue ball and do those sorts of calculations. With statistics, we kind of go the other way. We have one sample. So it's like, okay, I pick 2 balls out of the bag. I know what their colors are. What does this tell me about the contents of the bag? So we're kind of working in the opposite direction. Given some small sample, how can we extrapolate information from that sample to the larger population that we don't have data from everybody? So kind of the motivation here are the most common things that we might be interested in thinking about is like, what is the mean household income in the United States, something like this, or what proportion of people think that Congress is doing a good job when we do polling and things like this. So I want to kind of focus today on thinking about when we sample, when we're thinking about sample means, and when we're summing up things like how many people out of a sample of 1,000 feel a certain way. And so what I want to think about in particular is what happens to these predictions for large samples, for small samples, and what's the relation between these predictions and the sample size. So what you can think about is we have a population, and each of these xi's is representing a value that we pick from that population. So you might want to think about, just to consider the example we did last time, right? We can think of X as like a random variable representing, a randomly selected female's BMI from Israel. And then we can think about, well, what happens if we pick a lot of individuals at random from this population? And so we'll let like X1 is like the first person that we pick, X2 is the second person that we pick, and so on. And so we're going to assume that each of these people, each of these values that we pick are independent from the other. Okay, so in other words, the person that I pick first has no effect on who I'm going to pick second or third or fourth. And the second assumption is that we're picking all of these values from the same population. Okay, so I shouldn't be considering what's happening when I'm picking some females from Israel versus some females from another country, or males from Israel. These are different distributions. So we're picking all of these values from the same distribution. So when we're picking samples in this way, then we say these random variables are independent and identically distributed. And so when we repeatedly pick values or individuals in this way, then we say that this is a simple random sample. And what that essentially means is that everyone in the population has an equal likelihood of being picked. So I think part of the exercise today is we're going to be introducing some new notation. And secondly, we should have some intuition about how we expect these things to behave. And so I want to make sure that we're not totally surprised by what we're seeing. So I want to kind of start by thinking about this example where X is this distribution of female BMI in Israel, which is normal. We have a mean 26.5 with a standard deviation of 4.5. So this tells us what the population looks like. Right, and we've worked with how we can calculate probabilities from a normal distribution like this. And so now let's think about what happens if we pick randomly 100 women out of this population. So maybe we pick one woman and her BMI is 26, and then we pick a second and it's 30, and then we pick a third and it's 25, and so on. Okay, and so let's imagine we pick 100 women from this population. And we want to calculate the mean out of all of these 100 women. What would your best guess be? What do you think the mean BMI would be for these 100 women? Let's see, I got my chat covered up. Yeah, so someone said, so Christina, you said 26.5. Why would you think 26.5?
Because it's a normal distribution. So I would say that it would be symmetric and that it should, if you take any kind of random sample, it should have the same distribution, I would think.
So I think you're answering a slightly different question. Maybe saying like what you think the shape of the distribution might look like. But this, you answered more specifically, like why do you think we should expect to get that these samples are going to be about 26.5, these sample means?
Just, well, I would say just based on the normal distribution.
And so the 26.5, where did that come from? Welcome to hear from, I don't want to put anybody, one person on the spot. You've got the right idea. Just kind of curious about the rationale behind that. Anybody else? So let me ask you this. I'm going to pick a random sample of 100 men. And I'm going to calculate their height. What do you think is more common? That I'm going to get like 100 men have an average height of 5 feet, that they have an average height of 7 feet, that they have an average height of 5'10".
Probably 5'10".
What are you basing that intuition on?
looking at human beings. Most people aren't 7 feet tall.
Yeah, and so you would probably expect that your sample, if it's picked randomly, is going to resemble the population, right? It would be weird to have a population that has an average height of 5'10" and then pick a sample of 100 men that has an average height of 5 feet, right? So, I mean, it happens. Sometimes you just get like unlucky and you pick a sample that's not that representative of the population. But okay, most important thing you'll ever learn in this class, period, is the whole point of statistics is when you pick random samples, they are going to represent the population in an unbiased way. So if the population is 50% Democrat, 50% Republican, it would be really weird to pick a sample of 100 people and get, if it's random, and get 80 of them Republican and 20 of them Democrat. Okay, if you sample just your friends, okay, maybe you'll get a different result. Okay, but if you're doing this unbiased randomly, then what you're doing is you're just picking a subset of the population that should resemble the population in just about every way, except for the fact that it's smaller. Right? We just get some smaller version of the population. So our population here again is this distribution of BMI. So then you can imagine picking a sample of pick 100 women, and then from this sample, we add them all up, right? Divide by 100, and we should expect to get something close to 26.5. We should expect to get something that is close to the mean of the population. Okay, but there's going to be some variation, right? If I pick 100 women randomly, I'll get a mean. It should be about 26.5. Somebody else picks a different sample of 100, will get a slightly different mean, but again, it should be pretty close to 26.5. So if I'm picking one random sample of 100 women in Israel and I calculate that mean BMI, it's likely that that statistic is going to be the same as the population. Which is about 26.5. And so let's prove this more concretely. So I'm going to define this random variable x bar. And this is what's called the distribution of sample means. And so if I want to calculate the expected value of this new random variable, right? And so this is a random variable x bar, which is some function of all of these independent random variables, x1 up to xn. So plugging that formula inside there, right, that would just be the expected value of the sum of the x's over, we'll keep this general, over n. Okay, and then we talked about some properties of expected value. Mainly, I can pull out constant multiples and I can break up sums. So this is using the linearity of expected value. And since each of these x's is being picked from the same population, namely where the mean is 26.5, I know that the expected value of x, each of these x's, right, is 26.5. So altogether, this is going to give me 1 over n times n times 265, right? That corresponds to the n times that we're adding together 265. So what we can see here is the expected value of the sample mean is exactly equal to the population mean. That we just proved mathematically using that property of expected value. So just so you know, that we would represent with the same Greek letter mu, we would call that mu, and we put a subscript on it which just says this is the mean of the distribution of sample means. And what we just showed is that the expected value of the sample mean is equal to the population mean. So basically just restating the observation that we had in the first part. So we expect our samples to have about the same mean as our population. So I hope that's like an intuitive statement and it makes sense how we were able to kind of verify that using expected values. Okay, but any one sample is probably not going to give us exactly 26.5. And so this is the whole part of statistics, which is how much variability should we expect in our sampling process. So we'll want to get, that's the part we need to track down next. It makes a little bit of sense why I would expect my sample means to have a value same as the population. It's not as clear maybe to how we can consider how much variation we should expect from you pick a sample of 100 and why is my sample of 100 different than yours? So the two main distributions that we'll be thinking about are going to be sums and means. So these are going to be useful when we're working with proportions. Let me just say binomial sorts of things when we're counting things. And these are going to be useful when we're working with thinking about how a random variable where its mean is. So I want to start thinking about this one today. Any questions? Okay, so I want to play around with this website over here, which is linked, so you should be able to click on it. But if you're not, I'm just going to chat this into you all. And I think if you click on that, that should work too. And so this is a website that friends of mine create. They have a kind of intro stat book. And so I want to kind of play around with one of these data sets. So the data set that, and I think that it would be really good for you guys to experiment with this website. It kind of sinks in more when you're getting your hands dirty playing around with this rather than just sit back and passively watch someone tell you what the central limit theorem, which is this really, really powerful result in statistics. So when you open this up, they have some various preloaded data sets. The one I want to take a look at is called percent with internet access 3E. This just means third edition, means like the most updated data set that they have. So if you click on this, I realize that you guys aren't looking at my website, the website. Here we are. So you guys are looking at this, right? And the data set that I want to use is this percent with internet access third edition. So if this is a little drop down menu, and you can select different preloaded data sets. And what's happening is over here on the right, we have a dot plot. So we can see our population over here consists of 204 countries. So the N is telling us how many values are in this data set. So we have 204 countries. That's all of the countries in the world. And each of these dots is telling us what proportion of their, or what percent of their country have access to the internet. So we can see that this is not a normal distribution at all. It's almost more like a uniform distribution. So the population is not normally distributed, but I can see that the population mean is about 55%. Median is not as important here. And I can also see that the population standard deviation is 28.382. I'm just going to jot this down. So we've got the population mean is this 54.465. And we have a population standard deviation, which is over here, 28.382. And then, as we said, we can then think about, well, what happens if we generate a sample? So I'm going to hit the generate one sample button. And what happened is it picked a sample of size n equals 10. So you can see, first of all, we can play around with the sample size. By default, it's creating a sample of 10 countries. So there's a lot going on in this window. Up here is the population. In the middle is going to be what's called my sampling distribution. And then over here, this is showing me what this sample of 10 countries looks like. So it's saying here we had 2 countries that had about 13%, and we had some other countries over here. If we add up all of these values and divide by 10, we can see that this sample has a mean of 55.53, right? Which matches our intuition that it should be close to the population mean, but not exactly. And we get a standard deviation down here, which is also pretty close to the population standard deviation, but not exactly. So if I'm working, if you're looking at this worksheet, I can't show you both at the same time, but we're looking at question 2 on this worksheet, and it's asking, okay, out of these 204 countries, what is the value of mu, right? That would be the 54.465. The variance, right, is not going to be the 28.382. That's the standard deviation. So the variance would be the standard deviation squared, whatever that comes out to be. What do we get for that? Okay, and so picked one country over here. So I'm just looking down at question number 3, which is saying, okay, pick one sample. What are the mean, variance, and standard deviation of the 10 countries that I picked in my sample? So if you're doing this, you probably got something different. But my sample mean was 55.53. And my standard deviation here was 31.68. Okay, so any questions about what's going on here? What the difference is between the box that's in the upper right, the box that's in the middle, and what's going on in the box in the lower right corner? So I had a teaching mentor a long time ago who used to always tell me that teaching is an act of faith, meaning you just have to hope sometimes. You don't know whether you're reaching students or whether you've affected somebody. You just have to go on faith that you are. I think that the age of Zoom has put this, I have no idea who's out there. I'm just going to trust that the black boxes are okay with things. Because I can't see you and I can't hear you, so I hope you're okay with things. This is a big act of faith in me right now. There could be 9 people that are totally lost. So I'm going to take it on you guys to ask me questions if you have something that you're not clear about. Okay, and I am going to see you all 1 week from today on Monday. Black boxes are not an option. So then the next question is, well, what happens if we do this a whole bunch of times? So the worksheet's saying, well, let's do this. Let's generate 2,000 samples. So right there, I just generated 1,000. I just generated another 1,000. So now I have a big distribution here that contains 2,001 samples. So each of these dots down here is a sample, right? And that dot is corresponding to 10 countries that were picked. And then we calculated their average for the percent of people in that country that have the internet. And so as I click on different dots in the main distribution, you can see that the sample box in the lower right is reflecting which 10 countries were picked in that sample. So if I'm trying to describe, say, the whole shape of this distribution, meaning the one in the middle, what shape would you suspect that this distribution might have?
A standard distribution or like a bell shape?
Yeah, it's a bell-shaped distribution. It's not quite standardized, right? Because it has a mean and standard deviation other than 0 and 1, but we certainly know how to standardize that if we wanted to. Thank you. Yeah, so we've got a normal distribution. So it seems like this is bell-shaped. Not exactly, but a little bit. And if we want to get a sense of, so now we're thinking about the distribution of all of these sample means. Okay, and I can see that it's normal, and this little stuff down here is telling me what the mean of that distribution is. So in part B, so I'm looking now on the worksheet, question 4B is saying, let's compare the expected value of the sample means with the population mean. So we have that the population mean right, we found that was over here, was the 54.465. And then we have the mean of the distribution of sample means. And that we can see is this 54.547. And if you were randomizing this, you probably got something different, right? Not exactly the same thing that I got, not the 54.547, but probably 54 point something, right? Something pretty close to that. Okay, so the last thing to compare, and please let me know if you have any questions so far, is so far we're just looking at the shape of the distribution in the middle and comparing where this distribution in the middle is centered compared to where the population was centered. And next, let's take a look at how much spread we have in the values. So for the population, we have a standard deviation, which is up here. I've highlighted that on my window, which is like about 28. So the variance would be that thing squared, which comes out to like 500, or excuse me, 805 about. The distribution down here, I can see its spread is being described by what's called the standard error. And that comes out to be something much, much smaller than the population standard deviation. So what I can see here is that the spread in my sample means is much smaller. So here's where I'm working on this worksheet. So my first observation was that like the population mean, that was about 54. That's really close to the center of this distribution of sample means, which was also about 54. The population standard deviation, that we're going to denote with a sigma we use for standard deviation. Its therefore corresponding variance would be that 28 squared, which is about 805. comparing that to at least like the sampling distribution that we created online, that had a spread of 8.854. So the variance of this would be this 8.854 squared. So that's going to be about 78. So it's much smaller. Than the variance of the population. So here I can see that when we picked samples of size 10, our variance was 78, much, much smaller than that. So why might it make sense that the variance of the sampling distribution is smaller than the variance of the population?
Because there's going to be less instances of outliers.
Sorry, my volume was down low. Say that again, Karina. Something I heard the outliers at the end.
Yeah, would it be because there's less instances of outliers?
Possibly, yeah. So if you're thinking about like the standard deviation up here, or I keep forgetting that you can only see one window at a time. Let me go back. And we're going through this slowly because this central limit theorem is the most important theorem that we'll use this semester. So, you know, I think if you kind of just trust it and not really understand it, you're going to have a hard time this semester. Whereas if you kind of see where this result comes from, it'll be less of a leap of faith for you. And I think it'll be easier for you to apply it. But Karina is exactly right in terms of this 28 is measuring the spread of all of these individual countries. Whereas this 8.8, this standard error, is not measuring the spread in terms of like individual countries in the world, but it's measuring the spread in the differences of groups of 10 countries, right? So each of these dots is a group of 10 countries that we averaged together. And so although these samples look different, you know, I can look on the right and see there are different countries in each of these samples. Some of them are smaller, some of them are bigger, some of them are in the middle. But when we average those countries in the sample together, they're all going to be relatively good reflection of the population. So you're almost certainly going to get a question on the exam, which is going to ask you, explain to me why the variance of the sample means is less than the variance of the population. Just exactly what we're talking about right now. And let's see. So just to keep track of this different notation that we've had. So it's confusing because we have three different means already that we've been considering. We have the mean of the population. We have like X bar is used to denote what one single sample mean would be. And then we can think about, if we looked at the distribution of all of these different sample means, where would that be centered? And that's what this is denoting. So we see that the mean of the distribution of sample means is about the population mean. On the other hand, we have we use sigma to denote the standard deviation of a population. We use sigma squared to denote the variance we use S squared, so the Latin letter S, to denote the variance of one sample. So we have different sets of notation that we can use for different measurements of spread of different things. Yeah, and so there was a question about how is the standard error calculated. That's exactly what we're trying to get to right here, is what is the relationship between this and the population and the sample size. They're all related to each other. So hold on to that question. But I want to be sure that we're kind of certain about what each of these things are referring to. So when we use the sigma, the standard deviation of the population, this is looking at variability of individuals in the population. So in this example, individuals are countries. So it's thinking about across all countries in the world, how much variability is there in terms of internet access of different countries? And it's quite big. It's very variable because the world is quite big and countries are quite different from each other. So we're comparing things that are very, very different in some sense when we're looking at individuals. The standard deviation over here, right, this is measuring the same thing just across like one sample of 10 countries. Ultimately, what we're going to want to think about is how do we describe the variability in the sample means? So that's what this thing over here is. So this is measuring the variability and I should note here that we're dealing with random samples here. So this is denoting like how much variability should we expect from sample to sample. And since these samples are consisting of groups of 10 countries, there's less variability in a group of 10 random countries compared to another group of 10 random countries than we should expect from here's a random country, here's another single country. We might expect that those countries, if we just pick them at random, they're going to be quite different from each other. Whereas when we're comparing two samples of 10 countries picked from the same population, they're going to be more similar to each other. And that's the whole key of the central limit theorem. And so what we would like to get a sense of is, well, how much variability should we expect? If I want to come up with an estimate for the population mean based on a sample, how much error should I build into my estimate? So this standard deviation of the distribution of sample means is called the standard error. And so it might be written in different ways. So the standard error, sometimes we might write it just with an SE. Just keep in mind, this is exactly measuring the standard deviation of the distribution of sample means. That's a mouthful. So this is measuring the variability in sample statistics. Okay, so this is really abstract stuff that we've been talking about so far. And we'll see how we can apply this at the end of class. But are there any questions?
Yeah, would that standard error then decrease as n increases? Like if
Yeah,
you, with your
that's right.
size, sample size?
Yeah, so that's right. So now we might want to think about like, what is the relationship between the standard error and sample size? And if you think about it, you know, if I pick a random sample of 100 countries, what's going to happen to the variability in the sample statistics? Are the sample statistics going to become more uniform, or should we expect them to be more variable? And so we'll kind of see that by playing around with this website in a second. But that's exactly right. You should think about the larger that our samples get, the more they're going to resemble the population, the less variability we might expect in the sample statistics. So just to kind of, yes, you're looking at this, just to kind of look ahead for a second, that distribution that we had in the middle of the previous screen, that looked like this, except I made it smooth, right? Except it had lots of dots. This is what's called a sampling distribution. So each dot is a random sample consisting of n individuals, in our case, n countries. And what's important here is every sample is the same size. And what I would encourage you guys to do is not just know what the central limit theorem is that we'll summarize in this box, but kind of make sense about, you know, why these properties are true from an intuitive point. But the first observation is that this distribution is going to be shaped like a normal distribution. So what that's saying is, you know, most of the samples are going to look like the population. So if the population mean is, you know, in here, most of the samples are going to be stacked up in there. However, you know, it is possible that you get samples that are biased on the smaller end. Sometimes we just get unlucky, even when we're picking things randomly, and we get a sample that is disproportionate countries that had not a lot of internet users. And we're just as likely to get things that are biased in the other direction. over here, and the further we get from the middle, the less and less likely we are to get such extreme bias. So that's where the normal shape comes from. Most samples look like the population. You're equally likely to be biased on the small end as you are on the large end. And what's important here right? This is true even if the population is not normal, like our case, right? The distribution for countries in the world was kind of uniform. And even when we're picking from a non-normal distribution, we're still getting that the distribution of sample means is following a normal distribution. Okay, we've already discussed this observation that the center of this distribution is going to be centered at the value of the population mean. So most of our samples are going to have the same mean or close to the same mean as the population. And so what's left is to consider, right, what's happening with the standard error? How can we find the formula for the standard error? So let me just kind of summarize some things that we know. In this case, we know that the standard deviation for the population, that was about 28. When n was 10, I got a standard error, or maybe let me do this in terms of variance. So the variance of the population was 805. Sorry if I'm making you dizzy. So that's the variance of the population. And so when n was 10, we found the variance of the sampling distribution that was I think that was like 78. Is that right? Yeah. So this one is asking me to do it with n equals 30. So I'm just going to go, I'm not going to show you this, but all I'm doing is I'm going to reset the plot. I guess I can show you. So I just cleared it out, and I'm going to change n from 10 to now I'm going to set it at 30. And I'm going to generate 2,000 samples again. And now each of these dots in here, you can see consists of 30 different countries as opposed to 10. The shape is still normal, right? It's still centered at essentially the same place, the population mean, but now our standard error has changed quite a bit. It's gotten quite a bit smaller. So in this case, the standard error is we'll just call it 4.8. We're just about to put the cherry on top here for our completion of the central limit theorem. And all I need to do is calculate. You might have gotten something slightly different if you were playing around with this, because there is some variability at play. So the variance when n equals 30 is about 23. So we do see that when n is getting smaller, that's kind of the first observation. Sorry, when n is getting larger, it's not a good box. So the larger that n is, the smaller the standard error is becoming, because as the samples get larger, we're getting less variability from sample to sample. Does anyone see what the formula might be here? So the variance when n is 10, if I multiplied this by 10, we would get 780, kind of close to what the population variance is. If I take this variance, which was 23, and multiply it by the sample size, which is 30. Okay, we're doing some approximations here. We get something which is roughly equal to the variance of the population. So kind of the relationship here is that the standard error is equal to the variance of the population divided by the sample size. So that captures this effect that as the sample size gets larger and larger and larger, the standard error is getting smaller and smaller and smaller. When n is equal to 1, we pick samples of size 1, then the variance of the sampling distribution is exactly the same as the population, because picking samples of size 1 would just give us the population back. So we normally state this in terms of standard deviation. So what is true is that the variance is equal to the variance of the population divided by n. And so if I want to ultimately describe the spread of the sampling distribution with the standard error, then we just take the square root. Okay, so for example, if I knew that the population variance was 805, and I wanted to calculate the standard error for a sampling distribution that had size n equals 10, then I would take the variance, take the square root to get the standard deviation of the population, and then I would divide that by the square root of the sample size. So this gives us a way of theoretically describing what the sampling distribution is without having to go through those simulations. So to kind of summarize all of those bullets, we would say that the distribution of the sample means, this n is telling me that it's normal. This is telling me that it's centered, the expected value is the population mean. And this is saying we can find the standard deviation for this, which we call the standard error, by taking the standard deviation of the population, dividing it by the square root of our sample size. And this is what's called the central limit theorem. It's central to everything that we do in statistical inference. Any questions? Okay, so let's see how we could apply this to say answer a question like 6. So this is kind of where the content of the exam will end, like up to, but including questions like this. So you should expect a question like similar to 6 and 7 on the exam. So let's practice one of these. So we've got a population of BMI here for women, which is normal with our usual mean and standard deviation for that. And I do think it is really good to get in the habit of being particular about the notation that we use, because it's real easy to get confused between a population mean, a sample mean, and the mean of all the sample means. Using the right notation really helps us clarify to others which mean we're talking about. Okay, and so now this is saying this is the question that we're trying to answer here. So we're going to pick a sample of 60 for adult women. So that's our sample size. And this is asking us, okay, what is the probability that the sample mean will not exceed 1.125 BMI above or below the population mean? So I'm going to go where that 27.625 came from, that was 1.125 above the population mean. And I am going to need to use my calculator to subtract. So this is asking us how likely is it, right, that we pick a sample mean of size 64, and that mean is going to be between 25.375 and 27.625. Okay, and those values came from going above by 1.125 and below by 1.125. And so in order to calculate this probability, right, we don't want to use the population. We want to use the distribution for the sample means. So the big difference is we don't need to adjust where it's centered, but the sampling distribution is going to have a much smaller spread than the population. So we definitely need to make sure that we don't use the standard deviation for the population, but we remember to divide it by the square root of the sample size because we're working with sampling distribution of the mean. And so now at this point, what do we get? The 4.5 divided by 8. That comes out to 0.5625. So now this probability over here I can calculate using the p-norm function in R. So I could type p-norm, what's the probability that we're less than 27.625 where this is now centered at 26.5 and 0.5625. And again, the big difference is we use the standard error and not of the sampling distribution, not the standard deviation of the population. And then from that, we would then want to subtract p norm of the other one. So we could do that in one shot in R by taking the area to the left of the 27.625 and then subtracting the area to the left of 25.375. That would give us the area right between them. Okay, so I think what would be good homework for you guys to think about before coming to class next time is maybe take a look at question number 7 and give that a shot. The reading quiz for next time is really just focused on RStudio and making sure that RStudio is working well for you. So the video that I made for it is like 20 minutes long. You could probably focus on about 5 minutes of that video. So I did chunk it off. So depending on how detailed you want to be about RStudio, you're welcome to go through that. If you're kind of worried about, am I installing things correctly, and you want to hang around after class and just walk through a couple of things in R, you're welcome to. Otherwise, we've got office hours. Homework is due tonight. Otherwise, I'll see you guys on Wednesday. But if you do want some help making sure R is set up correctly on your computer, you're welcome to stick around. Otherwise, I'll see you guys on Wednesday.